we need to connect some of the statistics stuff to physics stuff, and the way we're going to do that is through temperature. So imagine that we're given two subsystems, A and B, in thermal equilibrium. A subsystem just means if we have a system A and a system B, and we define a bigger system that includes both of them with that red circle, then A would be a subsystem, B would be a subsystem of that larger general system. That's all I meant. So let's start by analyzing the probability that subsystem A is going to have a particular energy E sub A. You could imagine that the probability versus energy plot might look something like this. The details are not important. The important thing is just that it has some peak somewhere. That would be the maximum probability corresponding to the most likely situation where you'd find subsystem A having an energy E sub A. Okay, so how do we find that peak? Well, you probably know a calculus trick for doing this. Let's say that I want to plot out the slope of that graph, and I'll just start up near the top where I think the peak is. Then we follow the slope around, and at the very peak, of course, the slope is 0, right? So that tells us that the derivative of p with respect to EA must be 0 at that point. That's going to be the peak of our probability function. I'm going to put this in terms of partial derivatives so that partial p, partial EA is 0. That allows for the possibility that maybe the probability depends upon some other things that we didn't factor in. I'm only interested in its dependence upon energy right now. Okay, so we're going to start with that. So what is the probability of finding subsystem A with an energy E sub A? Well, we can write it out in terms of number of states, and I'll write this down and explain the terms. So omega sub A E sub A, that refers to the number of microstates at a macro energy E sub A. So remember, the idea is that you don't necessarily know by measuring what the number omega is, but you can measure an associated energy E sub A. We want to go through and calculate the number of microscopic states corresponding to that energy for subsystem A. Same idea for subsystem B. Omega B, EB, has to be the number of microscopic states for system B corresponding to a macroscopic energy E sub B. Now you may say, why does it matter what subsystem B is doing? Well, we're assuming that energy is conserved. So we need to conserve EA plus EB to be the total energy of our system, circled with the red line. That's why we have to introduce subsystem B, otherwise you could just ignore it. This is divided by the total number of states, omega total, and that includes both subsystems. All right, so we want to maximize the probability of finding subsystem A at E sub A. So how do we do that? Well, we already said, we just said its derivative with respect to EA equal to 0. Now, an interesting trick is that for a curve like the one I've drawn over there for the probability, it's also the case that we could take the derivative of the natural log of p and set that to 0. Why introduce natural logs when you don't have to? Well, one reason to think about it is that some of these omega values you can imagine are going to be quite large, and it'll actually be very convenient to take logs of these giant numbers so that we can manage them or put them into our calculator. Another reason is that taking the log actually lets us manipulate that fraction that represents p as a function of E sub A better than we could if it was just a normal fraction. You'll see what I mean in a minute. So we use the natural log version of this expression and say that 0 equals partial ln of p at E sub A divided by partial E sub A. And I'm just substituting in on the right the expression we already have for the probability of finding subsystem A at E sub A. Okay, now we can expand this out, right? Because that partial derivative is equal to 0, so 0 is the left-hand side, and we want to take the partial with respect to EA of the combination of all of these ln's. All I did was expand out the ln of a fraction. Okay, the nice thing is that last term, the ln of omega total, that does not depend upon the energy E sub A, so that's just going to be 0. It has no dependence on E sub A, so we'll just zero that one out. And if we rewrite that, we can also rewrite this energy E sub B in terms of E sub AB, the total energy of our entire system, that's circled with the red line over there on the left, minus E sub A, the energy associated with subsystem A. All I did was substitute in EAB minus EA for E sub B, which is fine because energy is conserved. Okay, so now we're going to move this up. And from here, what can we do? Well, let's actually distribute out the derivative. And at this point, it may seem a little weird to take the partial derivative of omega b with respect to EA. So I'm just going to treat that term separately for the moment. So that term on the right, we can actually rewrite it in terms of the partial with respect to EB, as long as we use the chain rule to also multiply by partial EB, partial EA. So that's all I've done over here on the far right, is to use the chain rule. Well, the nice thing is we can expand that out. So we'll keep the partial of omega b with respect to EB, but the partial with respect to EA now becomes EAB minus EA if we substitute back in, using conservation of energy, a different expression for E sub B. Why would I do that? Well, the nice thing is that this term, EAB, we can assume is constant. Now you may say, that's weird, why would you do that? The idea is that I've constructed the large system there with the circle over there on the left, assuming that we have some constant energy. Now the energy can change its partitioning between subsystem A and subsystem B, that's fine, but the total energy has to be fixed so that it does not vary with E sub A. Well, that's nice, because then its partial derivative with respect to E sub A has to be 0. The partial derivative of minus E sub A with respect to E sub A, that's just going to be a minus 1. So, long way of getting a minus sign out in front of partial ln of omega b with respect to EB. Now we can substitute this expression back in up here to our original expression. So we find that 0 equals the partial ln of omega A with respect to EA minus partial ln of omega B with respect to EB. I'm going to move this up, and I'll just write this in a more standard way by moving the negative term over to the other side. And look at that. The partial ln of omega A with respect to EA equals the partial ln of omega B with respect to EB. As I mentioned in the lecture notes, this is only really significant if you realize that 1 over the quantity, the Boltzmann constant times the temperature, equals partial ln of omega with respect to an energy. That implies that the temperature of subsystem A equals the temperature of subsystem B. Let me just walk through the logic once more. We constructed two subsystems, put a circle around them so that it was one large system containing both. We wanted to maximize the probability that if we measured subsystem A, we would find an energy E sub A. That's what we did by taking the derivative and setting it to 0. We had constrained the energy of subsystem B by noting that conservation of energy meant that their sum was fixed. That gave us the relationship ultimately that partial ln of omega with respect to energy for both of the subsystems must be equal. The tough part is realizing that that quantity corresponds to 1 over the Boltzmann constant times the temperature. In class, we'll come up with further evidence that this is indeed the case, and this is a statistical way of understanding the origin of temperature, namely that if you have two subsystems in thermal equilibrium, their temperatures must be equal.